In this video, we're going to focus on the graphs of the hyperbolic functions. So let's start with hyperbolic sine. Let's discuss the graph of this function. Now, hyperbolic sine is a combination of two exponential functions. It's e to the x minus e to the negative x divided by 2. So think of it as being 1/2 e to the x and then minus 1/2 e to the negative x. Or see it this way, see it as the sum of these two graphs. So 1/2 e to the x plus negative 1/2 e to the negative x. So what we're going to do is we're going to graph each of these components of the hyperbolic sine function. Let's start with 1/2 e to the x. So 1/2 e to the x is an exponential function that looks like this. Now, if that's 1/2 e to the x, what's the negative 1/2 e to the negative x? So to graph that, we could use transformations. First, let's start with negative 1/2 e to the positive x. Here, y is negative, x is positive. With this graph, we're reflecting it over the x-axis. So it would look like this. As you can see, this is a reflection of this graph over the x-axis. Now, if we were to plot negative 1/2 e to the negative x, add in this negative relative to this function, what's going to happen is we're going to reflect over the y-axis. So instead of this graph going this way, it's going to be going that way, like this. So that's the negative 1/2 e to the negative x. Relative to the original function, because we reflected it over the x-axis and the y-axis, the combination of that is basically reflecting it over the origin relative to that function. Now, e to the 0 is 1, so when you multiply that by 1/2, this point is at 1/2. This point here is negative 1/2. Of course, it's not drawn to scale, but that's what those values should be. Hyperbolic sine is the combination, it's the sum of these two functions. So when you add 1/2 and a negative 1/2, it's going to add up to 0. So at the origin, it's 0. Now, when x goes to positive infinity, in other words, as we move to the right, 1/2 e to the x is going to go to positive infinity. Negative 1/2 e to the negative x will go to 0. So when x becomes very large, this portion becomes significant. That is this portion. And this part of the graph it goes to 0. So what that means is that as we move to the right, hyperbolic sine, its graph is going to look like 1/2 e to the x when x becomes large. So it's going to follow this asymptote. Now, as we move to the left, as x approaches negative infinity, this part of hyperbolic sine, as we can see, it goes to 0. It becomes insignificant. This part goes to negative infinity as x goes to negative infinity. So hyperbolic sine is going to mirror this graph as we go to the left. So that's how we can graph hyperbolic sine from the exponential functions. The domain for hyperbolic sine is negative infinity to infinity. The range is also negative infinity to infinity. Now that we have hyperbolic sine already on the page for us, let's graph the reciprocal, hyperbolic cosecant. So knowing that hyperbolic cosecant is the reciprocal function of hyperbolic sine, how would you draw the graph for hyperbolic cosecant? When the y value of the hyperbolic sine function becomes very large, the y value of hyperbolic cosecant will be very small. So for instance, let's say this has a y value of 10. 1 over 10 is basically 0.1. In other words, as this goes up, hyperbolic cosecant is going to go towards 0. Now, as we approach the origin, the y value becomes smaller and smaller. So let's say over here where the y value is 1/2. For hyperbolic cosecant, the reciprocal of 1/2 is 2. Over here where the y value might be 0.1, 1 over 0.1 is 10. So as we get closer to 0, hyperbolic cosecant is going to go to infinity. It's going to become larger and larger. So at 1/2, it will be at 2. And as we move to the right where y increases, for hyperbolic cosecant, y is going to decrease. It's going to get closer and closer to 0. And as we approach 0, hyperbolic cosecant is going to go towards infinity. Now the same is true for the other side. Over here the values are negative, so hyperbolic cosecant will be negative over here. As we go towards negative infinity in the y direction, hyperbolic secant will go towards 0. As we approach 0, it's going to go towards negative infinity. So that's the graph of hyperbolic cosecant. It's a rough sketch of it, but I want you to understand how we get it from hyperbolic sine. By the way, the domain for hyperbolic cosecant, notice that x can be everything except 0. So if we look at it from the left side, it goes from negative infinity, we have a vertical asymptote at 0, and it goes to positive infinity. So this is the domain for hyperbolic cosecant. For the range, is the same thing. It goes down towards negative infinity. We have a horizontal asymptote at y equals 0, and then it goes all the way up to positive infinity. So this is the range for hyperbolic cosecant. Y could be everything except 0. Now let's talk about the graph of hyperbolic cosine. Hyperbolic cosine is very similar to hyperbolic sine, but instead of e to the x minus e to the negative x, it's going to be e to the x plus e to the negative x over 2. So we can break it up into these two exponential functions, 1/2 e to the x plus 1/2 e to the negative x. Now we already know the shape of 1/2 e to the x. It's going to look like this. At least that's a rough sketch of it. Now 1/2 e to the negative x, we have a negative in front of x but not in front of y. So it's only going to reflect over the y-axis not the x-axis. So that's positive 1/2 e to negative x. Hyperbolic cosine is the sum of those two functions. So at x equals 0, both of these functions have a value of 1/2. 1/2 plus 1/2 is 1. So hyperbolic cosine is going to start at a y value of 1. Now when x goes to positive infinity, this part goes to 0, this part goes to infinity. So hyperbolic cosine is going to mirror this graph when x becomes very large. So it's going to follow this asymptote. As you move to the left and go as x goes towards negative infinity, this part 1/2 e to the x goes to 0, as you can see here, and 1/2 e to the negative x goes to positive infinity. So this is going to have a greater contribution to this function when x goes to negative infinity. Therefore, hyperbolic cosine is going to mirror 1/2 e to negative x as you move to the left. Because this goes to 0, that goes to positive infinity. 0 plus positive infinity is just positive infinity. So that's the graph of hyperbolic cosine. The domain is all real numbers. X could be anything, but the range is limited. The lowest y value for hyperbolic cosine is 1, and 1 is included, so we're going to use a bracket, and it goes up to positive infinity. So now that we have the graph of hyperbolic cosine, we could talk about the graph of hyperbolic secant. Secant is the reciprocal of cosine. So looking at hyperbolic cosine, the graph for it, how would you draw the graph for hyperbolic cosecant? What would you do? So looking at this point, it's 1. 1 over 1 is just 1. So at 1, we're going to have the same point. Let's say this is 1 here. Now let's say this point has a y value of 2 and this point has a y value of 3. This point 2 will also have a y value of 2. This one will have a y value of 3. When y is 2, 1 over 2, if we take the reciprocal of 2, we get 1 over 2, which is a half. So at this point, it's going to be over here. It's going to be at 1/2. Now if we take 1 over 3, this will be at 1/3. And then 1 over 4th, 1/4. And so we could see what's happening here. As the y values go to infinity, as they get larger and larger, the y values of the reciprocal function is going to go to 0. Now the right side is a reflection of the left side. They're symmetrical, so this side is going to be the same. So hyperbolic cosecant will look something like this. So that's the graph of hyperbolic secant. It won't go past 1. As long as there's a 1 in front of this. If you put a 2 in front of it, everything doubles, so it'll go up to 2. But for unmodified hyperbolic secant, the range is going to be from negative, actually, hyperbolic secant doesn't go below y equals 0. So the range is going to be from 0 to 1. Now 1 is included. We have an actual point here, so we are going to have a bracket for the range of hyperbolic secant. As for the domain, you can see that it's our real numbers. Analyze it from left to right. X goes to negative infinity. It starts from negative infinity and goes all the way to positive infinity. So that's the graph of hyperbolic secant. Now, let's move on to hyperbolic tangent. If you've seen my previous videos, you know that hyperbolic tangent has three forms. There's this one, hyperbolic sine over cosine. And there's this form, e to the x minus e to the negative x over e to the x plus e to the negative x. And then there's this form, e to the 2x minus 1 over e to the 2x plus 1. Now, it's easier to graph hyperbolic tangent using this form of that function. So if we were to make a table, and let's say we were to plug in 0 into this expression, what would we get? So this would be e to the 0 minus 1 over e to the 0 plus 1. Anything raised to the 0 power is 1. So 1 minus 1 is going to give us 0. So hyperbolic tangent of 0 is 0, which means it touches the origin. Now let's look at the end behavior of this graph. As x goes to positive infinity, what happens to y? Well, this becomes e to the infinity minus 1 over e to the infinity plus 1. The minus 1 and the plus 1, they become insignificant. Now both of these are e to the 2x. They're going to grow at the same rate. And because they grow at the same rate as x increases, when x becomes very large, they will cancel, and this is going to approach 1. So as x goes towards positive infinity, y will approach 1. Now what about when x goes to negative infinity? What happens to y? So this will be e to negative infinity minus 1 over e to negative infinity plus 1. E to negative infinity is 1 over e to the infinity. And 1 over a large number is a small number, so 1 over e to the infinity is virtually 0. It gets closer and closer to 0. 0 minus 1 is negative 1, 0 plus 1 is 1, and this approaches negative 1. So when x becomes very large, y approaches 1, which means that we have a horizontal asymptote at 1. When x becomes very small, when it goes to negative infinity, y approaches negative 1. So that's going to be another horizontal asymptote. So hyperbolic tangent, as we go to the left, is going to get closer and closer to negative 1, and as we go to the right, it's going to get closer and closer to positive 1. So the graph, it looks like this. It passes through the origin, it starts from one asymptote, and gradually works its way towards the other asymptote. So that's how you can graph hyperbolic tangent if you know just one point, in this case the origin, and if you know the end behavior of the function. So now that we know the graph for hyperbolic tangent, let's focus on the reciprocal graph, hyperbolic cotangent. So what can we say about hyperbolic cotangent? Now over here the y value is 1. If we were to find the reciprocal of that, 1 over 1 is 1. But keep in mind, this is not equal to 1, but it's less than 1. So let's say if it's 0.9, 1 over 0.9 is a number that's close to 1, but just above 1. So what's going to happen is hyperbolic cotangent will have the same asymptotes at 1 and negative 1. The difference is As we get closer to 1, but we're still under or below 1, hyperbolic cotangent will approach 1, but it's going to be above 1 as opposed to below 1. So it's going to approach the asymptote, but from above it rather than below it. So it's going to be on this side here. And the proof of that is just, remember, 1 over 0.9. If you were to plug that in your calculator, I don't have one with me right now, it's going to be a number close to 1 but bigger than 1. And the same is true over here. Here it might be like negative 0.9. 1 over negative 0.9 might be like negative 1.1 or something. So what we need to know is that for hyperbolic cotangent, it's going to approach the asymptote, but rather than from within the two asymptotes, it's going to be outside of it. Now, as we approach 0 from the right side, let's say this is 0.1. 1 over 0.1 might be like positive 10. So as we approach 0 from the right side, it's going to go up towards positive infinity. As we approach 0 from the left side, this is not going to be like positive 0.1, but negative 0.1. 1 over negative 0.1 is like negative 10. So this is going to go towards negative infinity from the left side as we get closer to 0. So that's the graph of hyperbolic cotangent is going to look something like this. It's not a perfect sketch, but that's the general shape. It's outside of the two horizontal asymptotes, and because this goes to 0, we're going to have a vertical asymptote at x equals 0, because 1 over 0 is undefined. So now let's talk about the domain and range. The domain for hyperbolic tangent, we can see that it's all real numbers. As for the range, it's bounded by the two horizontal asymptotes. Now for hyperbolic cotangent, we need to incorporate the vertical asymptote. So looking at it from left to right, x goes from negative infinity, it stops at 0 at the vertical asymptote, and x can continue towards positive infinity. So we just have to take out 0. So it's going to be negative infinity to 0, union 0 to infinity. As for the range, we're going to analyze it from the bottom to the top. The lowest y value is negative infinity. Then it stops at this asymptote at negative 1. It starts back up at positive 1 and goes to positive infinity. So for the bottom half, the range is going to be negative infinity to negative 1, and it's going to stop there. And for the upper half, it's going to start at positive 1 and go to positive infinity. So that's the graph for hyperbolic cotangent of x. So hopefully this video gave you a good introduction into understanding the graphs behind these functions and how they work. Because once you understand where they come from, you can easily remember how to draw them, rather than simply relying on memorization.